We took that last semester. No? Yeah.
Hey. All right. Well, happy Wednesday. I didn't say that in lab usually. I do. And there's Katie. Okay. How was lab?
Awesome.
Awesome. I love it. This is probably the first time I hear it's such a positive.
This is so much fun. She was thrilled.
All right. Great. Do you want a TA next year?
For grad school.
Yeah. Oh, that's wonderful. Did you all finish? Did you all get your cookie label done? Okay, wonderful. That's great to hear. Like I said, if you have any questions as you write up your first lab report, please don't hesitate to ask, okay? All right, let's do some recap, finish up nutrition labeling, and move on to data analysis to this. All right, let's see. Is nutrition labeling required for all food? Yes, no, no. Give me an example of a food that we don't need nutrition label for, Emma.
Alcohol.
Again, okay. All right, a food.
Small.
Small candies, small packages also within big packages, and produce, meat, game meat, and eggs. All right. Let's see what else. What agencies regulate nutrition label? You can go wrong. Just name the one that you're most familiar with, William. FDA of the USDA. They regulate almost everything, with the exception of meat, poultry, and eggs, which is regulated by, yes, go ahead, Maddie. USDA, FSIS of USDA. Both FDA and FSIS are of the US. Okay. Very good. What type of analytical method? This is a common question I ask in a quiz or an exam. And a lot of students don't know what I'm asking about. What type of analytical methods are required to obtain the values listed on the nutrition label? We talked about categories, types of methods last time. So what do you think I'm asking here? Okay. I'm not asking for a specific name of a method. I'm asking you whether it is official methods of analysis or rapid secondary methods of analysis. What do we want to use? Go ahead. Official methods of analysis. They're also known as reference methods of analysis. They are called as primary methods of analysis because they are used to calibrate secondary methods of analysis. Okay. So that's what I mean when I ask what type of analytical method. I don't expect you to tell me a name of a method. It's a category, official methods of analysis. Okay. And by official, meaning they have been approved by an official organization, like AOAC, which stands for Association of Official Agricultural Chemists. Okay, that's one organization. What are new changes in nutrition label? The new nutrition label, how is it different? Go ahead, Alan.
The calories and serving sizes are much larger and bolder.
Yes, yes. What about a mineral that was added, Ali? Vitamin D, yes, it's the vitamin that's been added, and vitamin A and C was removed. Maybe potassium is the mineral that was added. We still have calcium and sodium, and iron, but they added potassium. There is one more important addition.
They added sugar.
Added sugars, yes, very good. Wonderful. When can you claim calorie free? Meaning less than how many calories you can say calorie free? 5. Yep. Is the label in compliance when an added nutrient level is at 80% of what is listed? When you add something, you're adding a calcium, or you're adding vitamin C. If what's on the label is about 80% of what is actually in there, or sorry, what's actually you measured is 80% of what is the label.
See greater.
Equal or greater than 100. Yes, when you're adding a nutrient, you're fortifying, you have to claim the exact amount or height. If it's a natural component, total fats, already natural component, it's okay. Well, actually, fat and calories and sugars should not be more than 120 of what the label says. So everything bad should not be more than 120. Everything good you added should be at least 100%. And anything already in the product, like proteins naturally occurring in that food, can be 80% of the label or more, but not less than. Okay, these things you have to remember. They're not too hard to remember. They're logical. Okay. So we have nutrient claims and there are health claims. They're two different things. Nutrient, it has to do with the actual nutrient. A good source of protein, a good source of calcium. That's kind of a nutrient claim. Whereas a health claim, it has to do with the health aspect. So the claim is associated with the health, like calcium, vitamin D, and osteoporosis. That's a health claim. So you have a physiological, whatever you call it, related to that claim that you are having. So, for example, low sodium and heart disease. Fiber and colon cancer. Things like that. That's health claim. Nutrient claim, it has to do with the component of the food, a nutrient of the food. Okay. So the nutrient levels, so we can say free, like sodium free or fat free, low in fat, lean, light. Light can be used for fat or calories. Reduced, less, a good source of, an excellent source of, and so on. And for all of these levels, they are associated with a certain percent reduction or a certain minimum daily value requirement. So you don't have to obviously to know, but when you are developing a product and you want to have a nutrient claim, you really need to know, is it 10% of or 20% of protein daily value I can then claim a good source of. So you would need to know these kind of numbers if you're actually developing those nutrient claims. But then for every component where you have a free, low, or reduced, the free, we already know, less than 5 calories, for example, for calories. Low, there is a reference. So you go 40 calories or less per reference amount. Okay. Reduced. So if you want to have a reduced claim for fat, reduced in yogurt, the amount of fat should be 25%, or calories in this case, 25% less calories compared to the full fat yogurt, for example, or full calorie yogurt. Has to be compared to the non-modified or the original reference. Of course, I'm not going to ask you to remember these values, but and actually your current textbook, the 6th edition, does not have to save on pages. We remove these tables, but I feel like they're good to know that there are references, FYI. You can find them in an older edition. You can also find them in Code of Federal Regulation. So, but I kept them in your slides because they're good references to know that, okay, for total fat also, less than 0.5 gram per serving or reference, then you can call it free. Reduced also is 25% less. So it's good knowledge, but I'm not going to test you on. And it goes on for saturated fat, cholesterol, all the bad stuff, sodium as well, sugars. But there are other tables for the good stuff, like good source of protein, good source of dietary fiber, stuff like that. Health claims, like I said, so they are specific to a condition, a health, a physiological condition. That was the word I was looking for, the physiological condition. Okay, so these are examples. There are many out there. And in order for us to have an approved health claim, it takes a lot of human studies and trials. A health claim doesn't go in effect without having a lot of studies, like NIH, for example, type of research that you would do on a lot of subjects so that you can prove that, yes, with a specific intake of calcium and vitamin D, we reduce the risk of osteoporosis. Once this is confirmed with clinical trials, then it can be approved to be put on the label. So you can't put anything you want on the label. It has to be an approved health claim. Okay, and we did the lab, so that is done. Any questions? Don't be shy. You're here to learn. So any question is a valid question. Why can't I see where my okay. And also questions, you get participation points. So do ask. Okay. So we will be analyzing data throughout the semester in all of the coming labs. So every lab, you will be generating data, simple or complex, and you will be analyzing this data, summarizing it, putting it in tables or figures, generating, doing multiple replication, calculating the mean, determining standard deviation, calculating coefficient of variation, and so on. Doing regression analysis. A lot of times we have standards, so you plot a standard curve and you use the equation of the line to predict a certain concentration in your product. So we will be doing that, and every lab will be unique. So that's why we're going to cover a lot of these terms. Some of these terms, you know them, you have them in your back pocket. You have done that in other places, even in middle school or high school, but we're going to do a refresher. In lab, we will also teach you how to use Excel to calculate some of these terms. Some of you are really savvy in Excel already. Some of you have not used Excel before. So there is a range, and we expect that you learn with us and ask questions. Okay. We talked a little bit about precision last time briefly. Let's see here. If method A is more precise in measuring glucose content than method B, which of these statements are correct? Yes, so we'll go with L. It's fine. Emma is reaching the probably already reached. both A and C. You know, it's partially correct. Let's hold that thought. Okay. Yes, it is just A. So the term for C is accuracy. Okay, you're not that far from, you always want to be precise and accurate. So the standard deviation is a term we calculate to see, usually when we do an experiment, we never do it once, we replicate. We have two replication is the minimum. Sometimes depending on the assay, we can do 6 replications, sometimes 20 replication. So every time we get a replicate, how close these replicates are to each other. So we're always getting similar results. So we are precise, or the method is precise. So the standard deviation will be lower if we're comparing similar means to each other. I'll talk more about that in a little bit. However, when your mean is close to the true value, this is also desirable, but we call it accuracy. Okay, so accurate, so close to what we expect. All right. So like I said, we do replications. And how do we evaluate our replications and our values? We always going to calculate the mean or the average. In this class, median is not really important. It's not like a set of data where we're looking at, let's say, distribution of grades. Then yeah, the median might be important. Half the class is above 70, the other half is below 70. But in the quantitative data that we get for this class, we measure the mean. Then we look at the reliability of the analysis. So accuracy and precision, we're going to talk about that. And the associated errors. We're going to learn about experimental errors and different types of errors that will impact our precision and or impact accuracy. Sometimes we're very precise, but we're way off. Sometimes we're really accurate, but our precision is not that great. Sometimes we're bad at both, not just us, but the method. And then we talked about specificity last time. Do you remember when we say this method is specific? What does that mean? Talk about method specificity. What does that mean? Do you remember? Can you give me one example we talked about last time? Do you remember, Marie? You were about to say something.
I'm not very specific about finding the glucose content, we select this comments.
Exactly. So if we're looking for total carbohydrate, we might not need a specific method for glucose or fructose or lactose. So how specific do we want to be in the analysis? What are we really analyzing? And then there are two terms that people often confuse with each other: sensitivity and detection limit. We'll get to that on another slide. A lot of the time you will have standard curves. So you will practice plotting standard curves. And in food analysis, mostly we do linear regression. Okay, we don't do exponential regression or other forms of regression, linear. So we look at correlation coefficient, how well the data fits a straight line. And then we look at coefficient of determination, or in other words, R squared, how well the equation of the line predicts the value that you're looking for. The higher the R squared, the better the prediction. Okay. And then we report the data. We're going to learn somewhat significant figures. You all have seen and learned this, but oftentimes students forget. You would write down whatever the calculator gives you or whatever Excel gives you to the 10th decimal after the decimal point. We don't do that. We only report significant figures. Sometimes we don't know how to get significant figure. We do a guess. So, but we'll talk about that later. And then sometimes you do 4 replications and one data point is way off, and it's throwing off your accuracy and ruining your precision. So there is a statistical way where you can actually throw out an outlier, something that is messing up your precision and accuracy. So we're going to learn about that as well. Okay. So this is just summary of what we're going to learn about. And then now I want you to take out a piece of paper, write your name on it, and I want to work with you on some refresher calculations, very simple. And then at the end of the class, you turn in that sheet. It's not going to be graded. We're just going to see that you solved and you get +2. That's an extra credit. So before you turn it in, just take a picture so that you have your correct calculations if you ever want to go back and study. All right. Well, here we go. Very simple. We're going to start from very beginning. Calculate mean and median. And when you have an answer, raise your hand. Lukman, you have an answer? For the mean, what did you get? 82.56. Very good. So what did you guys get for the median? Who wants to tell me? William, you have a median? 82.63. Yep, there it is. So we all know how to calculate an average. That's great. And the median is the number that is in the middle. And if you have an even number, do you know how to get the median? If you have an even number of replications? Yes, Emma?
2. Oh, wait.
Average the 2 in?
Yeah, the middle.
In the middle, yeah, exactly. When there is an odd number of replicates, that's easy. When there is even, when there are even number of replicates, then we take the 2 in the middle, average them, and the average is your median. All right, so you've seen this maybe before when you were in middle school, maybe. Okay, so tell me, A, is it representing good precision, bad precision, good accuracy, bad accuracy? Okay, handle. Exactly. So A is good precision, all your replication close to each other, but they're away from the dot. So they're not accurate. So you might be, that means you're a great researcher. Every time you're doing it right, but maybe your balance is not calibrated. It's always reading wrong. giving you wrong, systemic error. So you might have a real systemic error that you're not in control of that is causing you to be away from the accurate result. Or the method is not accurate for what you're trying to measure, no matter how good you are in your precision. Okay, B. What is B now? Go ahead, Emma. Yeah, so you are very precise and you're getting accurate results. So what about C? Who wants to say that's fun one? I want bad both. This is just like here, we're not even close. Either we're not following the method steps properly, we're using bad pipette, we have bad pipetting skills, something is off, nothing is working. And D is actually what D is. Okay, please. Yeah. So whatever we're doing, we're ending up when we average, we're ending up close to the true value, but our precision is not there. We're not using precise technique, or the method is not reproducible. Has a lot of steps and a lot of places where an error can happen, a random error can happen. Okay. All right, so now we're going to learn about how do we evaluate accuracy and then how do we evaluate precision. When we want to evaluate accuracy, we really need to know what the true value is. Sometimes it's a given. Like if you are using a 1 milliliter pipette, it has been mechanical pipette. It has been produced in a way that it should deliver 1 ml when you pipette 1 ml. So you know that the true value is 1 ml. Sometimes if you are determining protein content in a cheese product, then the true value would be whatever the label has on it in terms of protein content. Or the USDA website will tell you cheddar cheese should have this much protein. So you can get the true value from somewhere. Once you have your true value and you know what it is, then you do your experiments and you have your replicates, you calculate your mean, then the difference between your mean and the true value is your absolute error. So if you are very, very accurate, the difference can be 0. That's rare. Okay. And then you can calculate relative error. So the relative error is basically the same thing, absolute error, but relative to the true value. And then if you multiply it by 100, you get a % relative error. This tells you, for example, if % relative error is less than 5%, you are 95% accurate. So you have less than 5% inaccuracy. So this is pretty good. This means very accurate. If you have between 5 and 10%, that's very good too. If you have 20% error, that's not a good accuracy. All right, so the % relative error, the lower the better, but typically less than 5 is considered excellent. Between 5 and 10 is considered very good. All right, let's do some calculation. So that's the example of the mechanical pipette. 1 milliliter should be your true value. And then you're going to do that in the lab next week, is determine your precision and your accuracy using different types of pipettes or dispensing tools. One of them will be mechanical pipette. So practice those calculations. You can definitely get those values on Excel by plugging in the equations, but it's good to know. You might be asked to do that in a quiz. So it's good to know how to do these calculations. Usually the mechanical pipette is accurate to the third decimal. So it will be 1.000 milliliter. Anybody got the mean? Me, my sensor, not your timer. Devin, do you have the mean? 0.9961. Thank you. And we know what the true value is now. What is your absolute error? Lukman? 0.00339. Very good. What is the relative error? What? Same thing, because it's divided by 1. Yep. And then now percent relative error, you just multiply by 100. So this is very, very accurate. If you work in a lab, this is really important, especially let's say you're doing a tedious assay and you really need to use a mechanical pipette. You always have to make sure that your mechanical pipette is calibrated. So the way to test the mechanical pipette, if it's calibrated, you just take measurements and determine how accurate it is. If you end up having percent relative error over 5%, usually you want to make sure you send in people to calibrate or bring in people to calibrate your mechanical pipettes or send it out to get calibrated. That's why it's important. All right, standard deviation. Now this looks daunting, but it's not hard to remember, okay? It's good to remember this equation. So it's the square root of the summation. Xi is your 1 rep data point, okay? So rep 1, rep 2, or rep 3, or however. And X with the bar on top is the average. And then N is the number of replication. This is how you calculate standard deviation. It's not hard to remember. Good to remember so you understand how standard deviation is, what it means. So it's deviation from the mean, really. It's the summation of the deviation from the mean. Okay. And Excel sheet can calculate this for you. So you don't have in the lab or when you collect data and every time you have to determine standard deviation, you're not expected to manually do it. Excel can do it for you, but you're expected to know how it gets calculated. Coefficient of variation is most important for determination of precision. And I'll give you an example why coefficient of variation is in some cases more important than standard deviation. And basically, coefficient of variation, you take into account the mean. So you correct for the size of the mean. And this will make sense to you when I show you the example. So it's standard deviation by the mean, but it's a percentage. So you always multiply by 100. So it is, you always calculate percent coefficient variation. Percent of coefficient variation. Again, there is a rule of thumb, if you want to call it. If it's less than 5%, very precise, excellent precision. Less than 10, very good. Above 10, becomes questionable. You might have to redo your experiment. All right. Redo the experiment or see if there is an outlier in your data that you can throw up. All right. Let me demonstrate in which situation it makes a difference whether you calculate standard deviation or coefficient of variation. All right, we have two methods. In this example, you have two methods for protein determination. One is a secondary method using IR, that which requires calibration. The other method is DOMAS, which is based on nitrogen, determination of nitrogen, and it's an official method of analysis. And then you have two different types of samples. So two methods, two types of sample. This is going to happen with you in the lab where you are each group will be evaluating completely different types of samples using multiple methods of analysis. So we need to compare precision across samples and methods. Okay, so we have flour, regular wheat flour, and then we have soy protein isolate, which is an ingredient that is high in protein. The flour sample has 12% protein with a 1.2 standard deviation, and you tested that by NIR. The protein ingredient, soy protein ingredient, had a 92% protein and a standard deviation of 2.76. Which method is more precise? You want to guess, William? NIR. That's a very legit guess. But let's calculate coefficient of variation for each one of them. So if I want to calculate coefficient of variation, so I have percent, I need to get percent coefficient of variation. Standard deviation over the average times 100. All right, so for the flour sample, that my standard deviation is 1.2. My mean is 12. And then, so what is my standard deviation here is 10%, correct? Are we all following? All right, good. Now, if I want to get 30% of the other sample, so I have 2.76 over 92, and then times 100. What is this? Can you do the math? 3%? Good, +2 to you. All right, we got the +2. So 3%. Okay. Now, which is more precise? Which method is more precise? Dumas Golden, yes. So yeah, because now I have what happened here. Although, I mean, William's guess is a perfect guess, although this is lower standard deviation. But once I corrected for the average mean of that particular sample, then I can compare across different methods and different types of sample. If I don't correct for the mean, I won't be accurately comparing the two methods. I won't be doing a good job comparing the two methods if I'm only looking at standard deviation. That is the power of coefficient of variation, that term correcting for the size of the mean. We are correcting for the size of the mean. Then I can compare method A to method B, regardless of the type of samples I'm working with. And that's what you will be doing in lab, because one group will have baby cereal as a product. Another group will have cheddar cheese. Very different protein content. So how am I going to compare the different methods when I have different products? Okay, so you will be asked to calculate the standard deviation, because in order for you to calculate CV, you have to have the standard deviation. So you will always be asked to calculate standard deviation, then calculate the coefficient of the mean, and never forget that it is a percentage. It's a common error students do, is that they forget to multiply by 100, then your CV will be way off. So it is a percentage, and that's what you want to remember. All right. Confidence limit. You might remember that this is when you say, this is my mean plus or minus a certain value. That means the true value lies within this interval. That's what it means, the confidence. And sometimes your confidence, you choose, I want to be 90% confident. I want to be 95% confident. So that's your alpha. Okay, so is it 0.05 or 0.1? So you choose your confidence that you want. And then you would calculate the coefficient, the confidence interval, and then you will have a value plus or minus another value, which is the confidence interval. And you know that you say my true mean is within that range. Okay, so that's what it means. And you can choose again your percentage of confidence that you want, or the alpha. All right, let's do this exercise. Oh, before I go there, I just want to give you, in order to determine this plus or minus, you need either a t value or a z value, which you get usually from a table. And then the standard deviation over the square root of the replication n is, in other words, known as standard error. If you heard of that term, standard error is your standard deviation divided by the n. Then the t value, if you have replication less than 25, you need to get a t value. If you have more than 25 replication, you need to get z value. So for this, in your book, page 41 is what we need for the next exercise here. So if I have here how many replications? 3, then your n is 3. N minus 1 would be the degree of freedom. That would be 2. And then let's say I want a 95% level of certainty. Then the t value based on that table on page 41 would be 4.3. So 4.3, that's alpha is 0.05, and then degrees of freedom is 2. Then the table will give you that t value. Since we already know that you know how to get the mean, what is your standard deviation? Anybody with a standard deviation? Not yet. Anybody? Standard deviation? Standard deviation is taking what? Lukman? Zero, zero. 0.001 4. So the standard deviation should be 0.001. No, you must have an error here. Yes, it's 0.0019. So you might want to revisit your calculation. It might be a simple error. And then the coefficient of variation then? Anybody? Take a minute. So if the standard deviation is 0.0, just to remember, so standard deviation is the square root of the summation of xi minus the average. So you want to get the average and n minus 1. So n minus 1 in this case is 2. All right, and then you will, and this is squared. All right. So you have a CV? Maddie, do you have a CV? Yes, 0.19%. So CV is, again, your standard deviation divided by your mean, which is 1.9961 times 100. And you want to report it in two significant figures. We'll talk about 6 figures later, but you have to report it with 2 6 figures, so it will be 0.19%. And then did anybody get to coefficient interval? Take a minute, and then that will be the last thing you want to do. Did you calculate t times SD over square root of n minus 1 or n? You have that value, t times the standard deviation. You can do it right now. So 4.3 times 0.0019 over the square root of 2. What do you get on your calculator? Yes, Emma. How many replications did we have? Oh, yeah, sorry. Yeah. I'm sorry. You're right. N is 3. Sorry to confuse you. Yeah. We'll be out in a minute. Go ahead.
Have 0.004 something.
Yes. So you would round it up to two sig figures here. Okay. So then you can report your confidence interval as plus or minus this value, or you can add 0.0048 to 0.9961 and subtract it, so you will have a range. The lowest and the highest. So there are two ways of reporting it. Either put it as a range, the lowest number and the highest, or your average plus or minus. This tells you that whatever the true value is, it lies within this interval with a confidence of 95%. All right, I'll let you go. Thank you for staying a few minutes to finish that. Take a picture of your paper exercise and give it to one of our TAs. Either Yi can collect or Andresa. We can have a folder called extra credit, and then you save everything there. And then and Andresa put the separate as the paper.
Yeah, it's about that. It's up the hill. It's taxes. Spencer, read it. Oh, I didn't. I thought it was inside. Oh no. Just fun.